Hey everyone. So someday I should really come up with a bloopers reel because this is going to be take 2 on this video. Okay, so the purpose of this video is we're going to talk about linear functions and their graphs. So I'm going to start with a few definitions that are not on your worksheet. They're just kind of like filler definitions, and then we'll get to the actual worksheet. So we're going to cover a lot of stuff. We're going to look at what is a linear equation in 2 variables, what are solutions to linear equations in 2 variables, and then we're going to talk about methods for graphing. So we're going to look very specifically at graphing using intercepts, graphing using something called slope and y-intercept. We'll talk about slope, of course. Then we're going to look at horizontal and vertical lines and rate of change. Okay, so let's go ahead and get to it. So I'm going to go to the whiteboard. Okay, as always, there's a little bit of shuffling while I get settled. Okay, so again, take 2. So linear functions and their graphs. Okay, so like I said at the start, we're going to do a few definitions that are not on your worksheet. They're just kind of like background information, and then we'll get directly to the worksheet. The idea is that you've seen this at some point before, and we're kind of treating it like review, but I do want to give you some of that background info just so you're fully aware. So first of all, a linear equation in 2 variables is any equation of the form ax plus by equals c, where a, b, and c are real numbers. So that means a, b, and c can be positive, negative, whole numbers, integers, decimals, fractions, whatever. Where there is one condition, so a, b, and c can be any kind of number, where a and b are not both 0. Okay, I might change where to as long as or so long as or such that. That might be better, such that. Okay, so again, a linear equation very specifically in 2 variables. Now we're dealing with equations in 2 variables in this chapter. Okay, is any equation of the form ax plus by is c, where a, b, and c are real numbers such that a and b are not both 0. It's fine if a is 0, but then b can't be. It's fine if b is 0, but then a can't be. So at least one of those 2 values, a and b, needs to be non-zero so that we at least have an equation. Okay, so there's that first definition. Now solutions, we already know what solutions to equations in 2 variables are, but let's get specific about lines. So solutions to these equations will be the set of all ordered pairs that form the line. Now, generally speaking, we would say the solution is the set of all ordered pairs that make the equation true, and that's still the case. But when you're dealing with linear equations, those points that make the equation true happen to be all of those ordered pair points that form the line, okay? For that reason, there are infinitely many solutions. It'd be cool if I could spell, huh? There are infinitely many solutions to these equations. And what we're doing when we're graphing these equations is we're just looking at a snapshot of that equation. We're not looking at the whole line. Lines go on forever. There's no way we can look at the entire graph of an equation. So what we do is we kind of zoom in on one portion of the graph, so we kind of know, is the graph going uphill, downhill? Where does it cross the x-axis? Where does it cross the y-axis? Those are kind of the big things we're looking for, okay? So again, you've got the definition of an equation in 2 variables, a linear equation in 2 variables. You've got the definition of a solution. One thing I do want to point out about the equation, notice that you've got the 2 variables x and y, and what makes this linear is the fact that the exponent on the x and y are 1. If you had an exponent that wasn't a 1, it would no longer be linear, okay? So do keep that in mind. Now, as far as methods for graphing these equations, there's a few ways that you can graph lines. We're going to really look at 2 of them. We're going to look at graphing using intercepts, which I'll define in just a minute. And then we're going to look at something called slope-intercept forms. So to preface or to get us started on graphing by intercepts, let's talk about what are intercepts. So intercepts, generally speaking, are points where a graph crosses the X or Y axis. So if we're looking for X-intercepts, we want to know the point where the graph touches the X-axis. Excuse me. And then if we're looking for Y-intercepts, we're looking for points where the graph touches the Y-axis. So graphically speaking, we've got our Cartesian plane or the rectangular coordinate system here. Let's say we have this line right here that's in blue. This point right here would be your Y-intercept. This point right here would be your X-intercept. And let's talk about what that means. If I'm on the Y-axis, I never go left or right. So my X value is always going to be 0, and then I'm going to have some Y value. If I'm on the X axis, I never go up or down. Okay. So my Y value is going to be 0, and then I'm going to have some left or right X value. Okay. So that's kind of what our ordered pairs look like. Okay. So algebraically, how do we find them? So algebraically, locating intercepts. That's kind of what we want to look at right now. All right. Now, if you have a physical graph in front of you, it's pretty easy to determine what the intercepts are because you just look to see at what point does the graph cross the X or Y axis. If you're given an equation, you've got to kind of intuit what's going on. And that's kind of what this graph here in blue is all about. Okay. If you're looking for the X-intercept, okay, so the location of the X-intercept, we let Y equal 0 and solve for X. Okay. To locate the Y-intercept, we do the opposite. We let X equal 0 and solve for Y. Okay. So basically you let the opposite variable equal 0 and then solve for whatever intercept you're looking for. So if you're looking for the Y-intercept, you're solving for Y. Now with a line, you will have at most 2 intercepts. Okay, so at most you're going to have one X and one Y-intercept. There are situations when you have like horizontal and vertical lines where you're going to only have one intercept. So again, lines, you have at most 2, but some cases you only have one intercept. All right, so on the next slide, let's go ahead and look at an example. So the first example we have is to find the intercepts of and we have 3x minus 2y equals 12. So let's start with the x-intercept. So remember, you let the opposite variable equal 0 and then solve for, in this case, x. So I get 3x minus 2 times 0 equals 12. All right. So I get 3x minus 2. Well, that's just 3x. So 3x equals 12. I need to undo the multiplication of 3 and x. So I divide by 3. And that's going to give me x equals 4 because we get lazy and we say the 3's cancel. Just remember, when something cancels, it either becomes 1 or 0. In this case, 3 divided by 3 is 1. 1 times x is x. So I would write this ordered pair as 4, 0. So my x coordinate is 4 when my y coordinate is 0. Now let's look at the same equation, but we're going to look at the y-intercepts. Remember, let the opposite variable equal 0. So in this case, we're going to let x equal 0. And then we're going to solve for y. So 3 times 0 is 0. 0 minus 2y is negative 2y. Negative 2y equals 12. I need to undo the multiplication of negative 2 and y, so I divide both sides. Negative 2 divided by negative 2 is 1. 1 times y is y. And then 12 divided by negative 2 is negative 6. I would write this ordered pair as 0 for x, negative 6 for y. Please note, intercepts are 2 distinct points, okay? They're 2 totally different points on the line. So intercepts must be written as two distinct ordered pairs. Okay, now this question does not ask us to graph, but why not? Let's go ahead and graph this line. So remember, when we're graphing lines, we're just getting kind of like a snapshot of what is going on. I would also like to point out that I have very limited technology at my disposal, and I'm currently using my tablet, and it's not easy to switch back and forth. So I'm not going to easily be able to switch from the whiteboard in Zoom to like a Cartesian plane. So I'm just going to freehand. I'll do it as neat and clean as I can, just squint and pretend it's perfect. Okay, so my x-intercept is going to be on the x-axis. So at the origin, I go to the right 1, 2, 3, 4. I do not go up or down. For the y-intercept, it's on the y-axis. So at the origin, I do not go left or right. I just go down 6. And again, pretend this is absolutely perfectly drawn. And then we connect with a line. When you are graphing a line, make sure you put the arrows. Lines go on forever. We need to indicate that. So you can see this line crosses the x-axis and the y-axis at 4 and the -6. From left to right, it's going uphill, fairly steep. You got a pretty good idea of what this line is doing by just locating and graphing the y and x intercepts. Okay, let's look at the next example. So the next example, we are expected to graph this. So we are going to graph using intercepts. And we're going to graph -2x plus 4y equals 8. Okay, let me get a sip of water. And let's get to it. So remember, we're going to look for the x-intercept first. And remember, what you're doing is you're letting the opposite variable equal 0, and then you're solving. So I'm going to get -2x plus 4 times y, but we're going to let y equal 0. That equals 8. Now, 4 times 0 is just 0. -2x plus 0 is just -2x. So I get -2x equals 8. I need to solve. I need to get x alone. I do that by dividing by -2. -2 divided by itself is 1. 1 times x is x. And then 8 divided by -2 is -4. So I'm going to write this as -4 for my x coordinate and 0 for my y coordinate. Remember, intercepts are two completely separate points. They should be written as two separate ordered pairs. Okay, now for the y-intercept, I'm going to let x equal 0. So I get -2 times x, but x is 0, plus 4y equals 8. Well, -2 times 0 is just 0. 0 plus 4y is 4y. 4y equals 8. And then I need to solve for y. I do that by dividing both sides of the equation by 4. 4 divided by itself is 1. 1 times y is y, and y equals 2. We're going to write it as the x coordinate of 0, y coordinate of 2. And then we are expected to graph. So again, limited technology. I'm going to freehand squint and pretend it's perfect. Okay. My stomach is quite literally growling. If you hear it, just laugh and move on. Okay, so for the x-intercept at the origin, I go to the left 1, 2, 3, 4. I do not go up or down. For the y-intercept, I go back to the origin and I go up 2. I do not go left or right. And then we connect. And that's it. So that is graphing using intercepts. It's not a very difficult process. Generally speaking, finding intercepts is pretty easy. I will tell you this method is easy. It's very desirable because it is pretty easy, but there are situations where your intercepts are going to be really kind of nasty values. They'll be like fractions, mixed numbers, or decimals. If that happens, oftentimes graphing using intercepts is not the best way to go. So when your intercepts are nice integer values, like what we had for these two examples, intercepts are great. Otherwise, maybe find another way to graph. All right, next up is slope. Let me go back to the black pen. All right, so next up is slope. And for me, a very, very generic definition of slope is that slope is the steepness of a line. I have no idea if steepness is a real word or not, but we're going to pretend it is, because even if it's not a real word, everybody knows what I'm talking about. So it's the steepness of a line. It tells me if the line is really steep, not so steep, if it's vertical, if it's horizontal. So it gives us a number that indicates the, again, air quote, steepness. It tells us more though. The slope also tells us if a line goes uphill from left to right or if it goes downhill from left to right. So there's a lot going on here with the slope, okay? So this again is just kind of like the most generic definition. If you want to get a little bit more technical, slope is the ratio of the vertical, cool if I could spell, the vertical change to the horizontal change in a line. Okay, so again, it's just a ratio, and we're going to be looking at the vertical change compared to the horizontal change. So when we're talking vertical change, we're talking a change in y. And then if we're talking a horizontal change, we're talking a change in x. Okay, so let's kind of break that down further. So we know that slope, which is also denoted by a lowercase m, okay, slope is going to be, well, let me start with a definition, I guess, first. So I'm going to go ahead and say denoted by, again, a lowercase m, but then let's get the full definition here. We'll say the slope of the line through the distinct points x1, y1, and x2, y2 is, and now we'll get specific. So m equals, again, the change in y, that's our vertical change, divided by the change in x, that's our horizontal change. We call the vertical change the rise. So this right here is the formula that we will actually be using for the slope, okay? Now, you have two different situations that can happen. Well, four different situations that can happen. If m is positive, you're going to have a line that goes uphill. If m is negative, you're going to have a line that goes downhill, okay? If m is 0, we'll talk about this in a bit, you have a horizontal line. And then we can have a really wacky slope, which is undefined, and that occurs when you have a vertical line, okay? So if m is positive, uphill, m is negative, downhill, m is 0, horizontal, m is undefined, it's vertical, okay? So let's look at some examples, okay? So first what I want to do is just calculate some slopes, and then we're going to look at graphing using a slope and a y-intercept, okay? So examples, find the slope of the line through, and I'm going to write the directions once and then just repeat them. So the first example we have is we have a line that goes through the points -3, 4 and -4, -2. So I'm going to label these x1, y1, x2, y2. It does not matter which point you label x1, y1, which point you label x2, y2, just be consistent, okay? So m is the change in my y, so I'm going to take y2 and I'm going to subtract y1, okay? Because remember, our formula from the previous page is right here. So we take y2 minus y1, divide it by x2 minus x1, all right? And then x2 is -4, and we're going to subtract x1, which is -3. The biggest thing I tell students is watch your signs, okay? Especially when you're subtracting a negative, be extra careful. So for the numerator, -2 minus 4 is -6. For the denominator, I really end up with -4 plus 3 because when you subtract a negative, it becomes addition. So I get -6 over -1, and that simplifies to just plain old 6. So the slope of this line is +6. This line would be going uphill, and it would be fairly steep. So next up, we're going to have the same instructions, find the slope of the line through, but for this example, we're going to have the points 4, -2, and -1, 5. So again, let's say this is x1, y1, x2, y2. So m is the change in y's, so y2 minus y1 over x2 minus x1. Okay, so 5 minus -2 is really 5 plus 2. -1 minus 4 is -5. So let's see, 5 plus 2 is 7 over -5. I would just write this as -7/5. Okay, so this line, the first one goes uphill. So far, the second one goes downhill. Now, same instructions, find the slope of the line through, but this time our points are 1, 3, wait, 1, -3, sorry, and 1, -2. So same thing, x1, y1, x2, y2. M equals -2 minus -3 over 1 minus 1. Well, -2 minus -3 is -2 plus 3, but then the denominator is 0. So when the denominator is 0, it doesn't matter what the numerator is. You cannot divide by 0. This is a situation where we have an undefined slope, okay? Slope is undefined. Notice the x values were the same. That's going to happen when you have a vertical line, okay? So last example, same instructions, find the slope of the line through 2, -4, 5, -4. So we're going to say x1, y1, x2, y2. So m equals y2 is -4. We're going to subtract y1, which is also -4. x2 is 5. We're going to subtract x1, which is 2. So in the numerator, we get -4 plus 4. Denominator, we get 3. The numerator, -4 plus 4 is just 0 over 3. And how would that simplify? You can divide 0 by a number, so this just becomes 0. And this occurs when I have a horizontal line. And that should be fairly obvious because if you look at your y values, they're the same. Okay, so these are kind of the 4 different situations that can show up with slope. You can have a positive slope, a negative slope, an undefined slope, or a 0 slope. And just make note of what those slopes look like. Positive slopes go uphill, negative slopes go downhill. Undefined slopes are vertical lines, 0 slopes. And I am going to put here, don't say no slope. There is a slope and it is the value 0. 0 slope goes with a horizontal line. Okay, so that's kind of an overview of slope. This idea will come back later at the end of this, but for now, let's talk about slope intercept form of a line. Okay, if you solve a linear equation in 2 variables, for y, you get the following. You get something called y equals mx plus b. Okay, so you're going to get y equals, you're going to have an x term, and then you're going to have a constant. M, the coefficient of the x term, is your slope. Y, or not y, b, the constant is your y-intercept. Okay, so this is actually a really powerful thing. If you can take a linear equation in 2 variables and you can solve it, you get the slope and you get the y-intercept. So that's a lot of information. And this is easy to graph. So to graph, here's what you do. This would be true if you're graphing an equation with any point. Okay, so we specifically have the y-intercept, which is nice, but you could do this if you had any point other than the y-intercept. Plot the given point. So for us, the y-intercept, to apply the slope. Okay, so remember our slope can be thought of as rise over run. So we would go up or down, and then we would go left or right, depending. Okay. And so then you want to plot 3 or more points and then connect with a line. Okay. So it's not necessarily difficult to graph with any point in a slope. Okay. You can do that. Literally, I could give you any point on a line in the slope. You plot the point. From that point, apply the slope, go up or down according to the numerator, go left or right according to the denominator. Do that a couple of times. Plot, I like to plot 3 points, connect with a line, and you are done. Okay. So what's really nice about slope intercept form of a line is you get enough information to graph really quickly, really easy. And earlier we looked at graphing with intercepts and it was super easy to do, but if the intercepts are kind of wacky, like if you get decimals, fractions, or mixed numbers, it's not as easy to graph with intercepts. This method is never going to be that bad. Sometimes you could get a weird y-intercept, which would make this more difficult, but generally this is kind of like the go-to method. Okay. Now recall, I'm going to give you a linear equation in 2 variables, and I'm going to remind you how to solve it for y. This is not on your worksheet. This is just extra info. So let's say we had something like 3x minus 5y equals 20. Okay. If I needed to solve this for y, I first want to isolate the term that contains the y. So the issue is this plus 3x. I would move the 3x by subtracting it from both sides. On the left, 3x minus 3x is just 0. 0 minus 5y is negative 5y. And then on the right, I cannot combine negative 3x and 20, so I'm just going to write them out. And I do want to put the x term first because I want my x term, then my y-intercept term. So I'm going to do negative 3x plus 20. And then finally, I want to get the y alone, so I would divide every term by negative 5. I think it's easier if you divide all the terms instead of just both sides. It simplifies easier. So 5 divided by 5 is 1. 1 times y is y. Negative 3 divided by 5, I want to leave this in fraction form, so I don't want to write this as a decimal or anything. I do just want to simplify my signs. So I get 3 divided by 5 positive times x. And then finally, for my constant, I get 20 divided by 5, which is negative 4. So that's just a quick reminder of 1, how to graph using a point and a slope, and 2, how to solve for y. So recall, and I am going to put here solving for y. Okay, so let's get back to the worksheet. We're going to look at an example of graphing using a point and a slope. So graph, and we're going to use slope. Well, I'm going to write it like it's on the worksheet. So use slope intercept form to graph the line. And the line we're going to graph is y equals 2/3 x minus 1. Now, let's talk about some stuff. We have m equals 2/3. In this form, it tells us that we would go up 2 and to the right 3. But notice if we go back a slide, notice when I was like right here, I originally had negative 3 divided by negative 5, and that simplified to be positive 3/5. You would want to simplify it, but just know negative 3/5 is equal, or negative 3 divided by 5 is equal to positive 3 divided by positive 5. So if I go back here, I could also treat this as negative 2 over negative 3, and that would tell me to go down 2 and then to the left 3. So I do want you to understand that you can apply your slope in 2 directions, and I'll show you that when we do this graph. Okay, now b is the constant. So the constant here is negative 1, and that just translates to the ordered pair 0, negative 1. Okay, so remember limited technology. I'm going to do this as neat as I can. You're going to squint and pretend it's perfect. Okay. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to go out 8. That'll be plenty. And 1, 2, 3, 4, 5, 6, 7, 8. Okay. So you want to start by plotting the point you know. We know this point right here. It is on the graph. So at the origin, I do not go left to right. I just go down 1. And that makes sense that this is on the y-axis because remember, b, the constant here, is going to be your y-intercept. From this point, I want to apply my slope. So I'm going to start by going up 2. So up 1, up 2. And then I'm going to go to the right 1, 2, 3. That point has to be on the line. But what if instead of going up 2 to the right 2, I went down 2 to the left 2, or to the left 3? So let's say I go down 1, 2, and then to the left 1, 2, 3. Well, that point is still on the line. So you can apply your slope in 2 different directions. So if you kind of run out of room in one direction, try the other direction, okay? I like 3 points. 2 points makes a line, but I like to do 3. So there you have it. So again, when I do slope intercept form, I'll generally apply the slope in both directions. That gives me 3 points. Again, 2 points is fine. You only have to apply your slope once. I'll generally do it twice though. So that's it. So this is the graph of the line that represents the equation y equals 2/3 x minus 1. Let's try another one. So again, we're going to use slope intercept form to graph. Let me go back to black ink. So use slope intercept form to graph the line. This time we have y equals -1/2 plus, -1/2 x plus 3. Okay. So let's figure out, this is already in slope intercept form. It's already been solved for y. Just remember 2 slides ago, I showed you how to solve for y. If ever you're given an equation and it says graph using slope intercept form, you have to solve for y first doing this stuff right here, okay? But luckily this example and this example have already been solved for y. So first let's determine what our slope is. So we have m equals, well, it's the coefficient of x, and we currently have -1/2. This tells me to go down and to the right, or if I did 1 over -2, it still equals -1/2. That would tell me to go up and to the left. So I am going to apply this slope both directions so you can see how it works. B, the y-intercept, which is the constant, is the 0.3, or it's the 0.03. So let's graph. Again, remember limited technology, squint and pretend it's perfect. I can already tell that one's like way not perfect, so I will fix that one. Okay, again, pretend it's perfect. So we're going to plot the point that we know, which is the y-intercept. So at the origin, I don't go left or right. I do go up 3. From that point, I want to apply the slope. So from the y-intercept, I'm going to go down 1 to the right 2. I could go down 1 to the right 2. All 3 of those points are on the line, but I could also invert the slope, and not invert the slope, but invert that like negative. And instead of going down, I could go up and then to the left 2. Notice all of these points are on the same line. So you can apply that slope either direction. Again, I like to generally apply it twice when I'm doing slope intercept form. And there you have it. This is the graph of the line that represents the equation y equals -1/2 plus 3. Cool. Now, next up, we're going to talk about horizontal and vertical lines. I do want to remind you of a definition. I'm going to give you a little background information here too. Okay. So I'm going to say recall. There we go. A linear equation in 2 variables. Is any equation of the form ax plus by equals c, where a, b, and c are real numbers such that A and B are not both 0. Okay. Now it's okay if one or the other is 0, they just both can't be 0 at the same time. When one or the other is 0, that's when we get horizontal and vertical lines. Okay. So if A is 0, X disappears, leaving by equals C, or if I solve for y equals C over B. This is a horizontal line. And I'll tell you more about that in just a second. But just know if A equals 0, this X term up here, it disappears. You're left with by equals C or y equals C over B. That's when you get a horizontal line. If B equals 0, y disappears, leaving AX equals C or X equals C over A. This is when you get a vertical line. Okay, so just know there's a rhyme or reason to this definition that I gave you at the beginning of the video, and that whole when A and B are 0, something happens. That's what causes us to get a horizontal and a vertical line. Okay, so that's kind of your background information. Let's get back to the worksheet. Okay, so looking specifically at horizontal lines. Okay, we have that they are always in the form y equals b, where b is the y-intercept. So once you have an equation that just has a y in it, if you solve it for y, that constant that you get is going to tell you where you cross the y-axis. Okay, we already know that the slope of a horizontal line is 0. Okay, and let's say that we have the example y equals 2. Well, if I wanted to create a table of values, I know that y has to always be 2. Doesn't matter what x is. Let's say x is -3, 0, and 5. Okay, we just know that if we have y equals 2, the only thing y could ever be is 2. So let's look at this graphically. Again, pretend this is perfect. Squint your eyes if necessary. Okay, so if I plot these points at the origin, I go to the left 3, up 2. At the origin, I stay there and I go up 2. At the origin, I go to the right 5 and I go up 2. You can see here that we have the horizontal line y equals 2. Okay, so just know this information here, you're going to be in the form y equals some constant. That constant b is the actual intercept. And here's an example and a graph that you can look at. Okay, and just going back, remember, a linear equation in 2 variables is an equation of the form ax plus by equals c, where a, b, and c are real numbers, such that a and b are not both 0, but in the event that a is 0, x disappears, leaving by equals c, or y equals c over b. C over b, since a, b, and c are just numbers, that's just going to be a constant. So you're going to get y equals some constant. That's your horizontal line. Okay, so let's look at vertical lines. I keep forgetting to go back to my black marker. Sorry about that. Okay, so vertical lines, okay, always in the form x equals a, where a is the x-intercept, okay, and then the slope of all vertical lines is undefined. Okay, remember that's kind of the wacky one. Now let's say that we had x equals -3. If x is -3, x can only be -3. Doesn't matter what you choose for y because you don't have a y in the equation. So it's kind of almost like you have x plus 0y equals -3. Doesn't matter what you plug in for y, it's going to zero out. Okay, so let's say we do -2, 0, and 1. Okay, let's graph. Again, we're going to pretend this is absolutely perfect. So we would do at the origin, we would go to the left 3, down 2. Well, down 2. At the origin, we go to the left 3 and then we'd stay there. At the origin, we go to the left 3 and then up 1. We can see these 3 points create a vertical line. Notice this has only one intercept, and it is the point x equals 3. Okay? So there you have it. That's horizontal and vertical lines. Again, if we go back a couple of slides, the linear equation in two variables is any equation of the form ax plus by equals c, where a, b, and c are just any real number, such that a and b are not both 0. In the event that b is 0, your y term disappears. It just becomes like this. It becomes like ax plus 0y equals c. So then this kind of theoretically disappears and we get ax equals c. If we solve for x, we get x equals c over a. This is just a constant. And the x-intercept, it just so happens to be, okay? So if we go back to our most recent slide, there you have it. That's the information you need to know about vertical lines, okay? Now, for the last graph, or for the last thing we want to cover, we want to talk about slope as a rate of change. Okay, so recall slope is the ratio. Ratio just means you're dividing one by the other. So it's the ratio of the change in y to the change in x. Okay, we can think of this as a rate of change. So quite literally, m equals the change in y over the change in x. And just remember, that's y2 minus y1 over x2 minus x1. So what we have is we have a graph, and it shows the average age of your first marriage in the United States for men and women between 1970 and 2015. I'm going to give you just a rough graph, okay? This is women. Men, okay, we have 0, 23.2, 45, 29.2, and again, this is men. So this is kind of just a rough estimate of the graph. This x-axis represents the years after 1970, and the y-axis represents the age, okay? I'm not going to fill in all the other details, just know this. So again, this represents the age of first marriage for men and women from 1970 to 2015. It shouldn't be that surprising that the age of marriage increases. Like in the 70s, my parents got married when they're 18. I'm not 18 and I'm still not married, and I don't plan on it anytime soon. So I think as time has passed, we're getting married later and later in life, okay, on average, okay? So let's look, oh, hold on one second. So this does happen, hang tight. I really hate this because I'm going to lose my graph, but sorry. it only lets me do like 10 or 11 slides, then I have to go out and go back in. So sorry about that. You get to see my shining face again. Now, the upsetting part of this is I've lost all of my previous slides and I just drew this graph. But basically, the heart and soul of this is we're looking at women. And in 1970, 0 years from 1970 had passed, and the average age of women getting married was 20.8. And in 2015, the years after 1970, where 45 years had passed, and the average age of marriage was 27.1. That's the heart and soul of the information you need here. So we need to answer some questions about this. It says, use the given 2 points to find the average rate of change for women's first marriage. So we're going to find the average rate of change for women's first marriage. Okay, so we're going to call this x1, y1, this x2, y2. So m equals y2 minus y1 over x2 minus x1. So I'm going to get 27.1 minus 20.8 over 45 minus 0. I am going to get a calculator because this is going to be nasty. So when we simplify, 27.1 minus 20.8 is going to be, that's not even remotely correct. It's going to be 6.3. 45 minus 0 is 45. And if I divide this out, I get 0.14. So the age increases by 0.14, so like 0.14 years each year from 1970 to 2015. So this right here is your rate of change. And again, the age increases by 0.14 years every year from 1970 to 2015. The second question we're asked is to create a function using the data from part A and the graph. Well, we know that the slope is 0.14. We know that the y-intercept occurs when x is 0. So the y-intercept is going to be 0, 20.8. So if this is my slope and this is my b, I can plug that into y equals 0.14x plus 20.8. Now, if we're going to get really technical, the age increased by 0.14 years each year until 2015. So part C then says, use the function that we just created in part B to predict the average age of marriage of the first marriage. And again, this is for women in 2030. So ask yourself, how many years have changed from 1970? So 2030 is 60 years from 1970. All right, so remember, X is the number of years from 1970. I would love to show you this in the graph, but those slides are long gone. So we would get f of 60 equals 0.14 times 60 plus 20.8. Plugging that into the calculator, I get 0.14 times 60, which is 8.4. I'm going to add 20.8, and I get 29.2 years. So by 2030, according to this data, the average age of a woman's first marriage will occur when she is 29.2 years old. Okay. So again, sorry, I should have been a little more careful with my slides. When I use my tablet, I have a limited number of slides that I can create. All right. So it was kind of unfortunate timing that it happened after I drew the graph for that problem, but you can rewind the video and go back and see what the graph looks like. Okay. So that is a lot of talking. Let me get some water. So that is linear functions and their graphs. Okay. Hopefully this was a lot of review. This is stuff that you technically should have seen when you were in like a high school class, okay? If not, watch the video a couple of times, read in your textbook, look at videos in Pearson, do whatever you need to do, okay? Ask questions. If you're stuck on anything, please reach out, all right? Take care.